All right, so let's expand on that 2-unit idea. Further growth and decay. Now, in reality, there's external conditions that come into play in these models. The classic one is temperature. If we think of temperature rather than population, and things cooling down or heating up. But the temperature of an object, if it's just left to its own devices, will never go, if it's cooling down, it'll never go lower than room temperature, and if it's heating up, it'll never go above room temperature. Okay? That's if it's left to its own devices. Obviously, if you put it in a fridge or on top of a stove or something like that, that's then applying some more external conditions. And so, yes, of course, it then could. So we've got to change our equation to take this into account. So the P to T will now equal K times P minus N, instead of just K times P. So that minus N in there is taking into account the external conditions, the room temperature or what have you. Now, the solution to this one, I didn't bother going through and proving it like the last one, but I'd do exactly the same thing. You know, I'd turn it upside down, integrate it, it'd become a log function again. There is the trivial case, which we don't worry about, but it is theoretically a possible solution, that P is equal to N. Now, if P is equal to N, what happens to P to T? Yeah, it's 0. Which basically means there is no change, and so that's why P ends up being a constant value of N. The trivial case, we don't worry about it, not interested in that. The other possibility is this one, P equals N plus AE to the KT. Now imagine we were drawing the graph. Remember the 2-unit model didn't have the external condition, it was just P equals AE to the KT. So a basic exponential curve. What's the difference with this one? Right. And so that is that external condition. Remember I said, so it's an exponential graph. Say it's cooling down and it will never go below the room temperature. So instead of going asymptotic to the axis, it's going asymptotic to whatever the room temperature would be. And so that N there must be that external temperature, if we're talking about temperature. That's where the graph is going asymptotic to. So P would be population at any time. N plus A is the initial population. K, again, is our growth or decay constant. T would be time, and I don't think I put it there, but as I just said, N would end up being that external condition. So here we are, 1993, a while ago, but it's a classic question. Good old Newton, he did so much for us. He even gave us these sort of questions as well. So T is the temperature inside the room at time little t. A is the outside air temperature. Newton's law of cooling states that the rate of change of temperature is proportional to T minus A. Show that T equals A plus C to the KT satisfies Newton's law of cooling for the first part of the question. So again, I just need to show this satisfies that the derivative, the rate of change, is proportional to T minus A. So there's T. Differentiate it, well A is a constant, so that goes to 0. Exponential, so K comes out the front. I have KC. However, we know that T minus A is CE to the KT, because if I rearrange this equation, I'll get T minus A is CE to the KT. So I can substitute in, and there it is. My rate of change is equal to some constant times T minus A. So it's proportional to T minus A. So it does satisfy our equation. So that's nice if they ask that first. There's a little bit of a gift question at the start. All we're going to do is do a little bit of differentiation, rearrange it, and we've got ourselves a mark. All right, outside air temperature, 5 degrees Celsius. It's a pretty cold day. But the heating system has broken down. Oh no! Causing the inside room temperature to drop from 20 to 17 in half an hour. And everyone's screaming, fix the air conditioning, fix the air conditioning. After how many hours will it drop down to 10 degrees and everyone's crying? It's so cold. T will end up equaling then 5 plus C to the KT. Remember? That 5, the asymptote that is going down to the outside room temperature, that's where it's, so they've told us that is 5. So I know my equation is 5 plus CE to the KT. But they also told me the initial one, we're starting at 20, So C will be 15. Now we said that, what pronumerals did I use in it? But anyway, those two constants added together to give the initial temperature. So 5 plus 15 is 20. What else do we need to work out? We'll need to work out our constant. So we should have some conditions we can sub in. And what have we got? The outside, in half an hour, it drops from 20 to 17. So when T is 0.5, capital T is 17. So 15e to the 0.5 K is equal to 12. Playing around with that to make K the subject, and there it is. K is 2 log 12 on 15. Again, it's a decay one, because we know that's the log of a number smaller than 1. All right, when T equals 10, we want to find out how long that takes. So we need to make little t the subject of our exponential equation. So take 5 from both sides, divide by 15. So T will be 1 on K, that number we just worked out, log of a third. Subbing that in, we get about 2.46167. So I said about 2.5 hours. 2.5 hours. All right. So that's really the only difference between the two. In 3NET, we add in that extra condition. So we shift the curve up, basically, or down, depending on the problem. 7H, 1, 2, 3, 6. I'm still feeling like I haven't given you enough to do.